In this video, let's continue to look at a few more ideas and problems that put our ideas about derivatives to work. Okay, so here we have a piecewise defined function f of x, and you see four different pieces here, but this is actually one function. I've graphed all four pieces in different colors, but probably it should all be the same color because it's one function. Okay, and let's say there's a solid dot here, an open dot up here, and solid dots here and here and here. Okay, now can we come up with a formula, or not a formula for this, but can we come up with a graph of the derivative? So let you think about that one a little bit and see what you can come up with, and then come back when you think you have a graph drawn. Press pause now. Okay, well, let's start with the easiest part. This is horizontal right here, so the slope is 0 everywhere. So on this little piece, the derivative is 0 all the way across here. Now we have some place at this place. Let's look at this. This is a straight line which has a constant slope, and if you can look at the scale here, the grid lines are spaced 1 apart in every direction. So if we find a point on the grid line here, when we go the right 1, we go down 2. You see that's a constant. So this has a slope of -2. So the graph here of the derivative would be down here at -2 from here, this point, straight across to here. So you got a straight across little line sigma here. Then you got a break where the derivative is undefined at this sharp corner, and it goes across here at 0. Because of the discontinuity here, we also have a break. A derivative is undefined when x is 0. Now this part's a little harder to see, but we over here, let's see, first of all, the red part over here, this is a negative slope, so we should have seen a negative derivative, and we did. It was -2. This is horizontal, so constant, so we saw a 0 slope, so the derivative was 0. Here the derivative is negative because this function is decreasing, and it actually goes from 0 and then it comes down from there. So it actually starts at 0, and it's actually undefined right here because of the discontinuity. So you have an undefined point there, and then it comes down this way. And you'd have to just estimate some values here to see what it would be. So for example, right here, it does level out to be about 0 there. Right here at 1, let's see, if you go the right 1, it goes, let's see, be here, and left 1 to do the symmetric difference quotient. Let's see, we're looking at a y value of 10, dropping down to about 6. So that's a drop of 1, 2, 3, 4. And a delta x of 2, so that's a -2 slope. So that slope, that would be 1 and -2. There'd be a dot there. Okay, let's look what would happen right here. Again, if we go right and left 1, let's see to the left, you're up here, and the right down here. Let's see how far that drops. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12 actually. So that drops 12, so delta y is -12, delta x is 2, so that's 12 over, -12 over 2, that's -6. So that would be 3, -6, and so forth, and we could plot some points there. So it's kind of coming down like this. Okay, we'll look at that in a minute. Now, this part here, at the maximum here, the derivative is 0, so that's going to be right here. On this piece, the derivative is positive, and on this piece, the derivative is negative. So to the right, just to the right of 7, the y values on the derivative are going to be negative numbers, and they're going to be positive numbers to the left, and we're actually approaching infinity, at least from one side here, and negative infinity over here. So actually, it's going to cross the axis right here at 7. It's going to come down from infinity like this, asymptote. It's going to level out, and it's going to come back down. So here's the actual derivative function here. So this horizontal piece had a slope of 0. There it is. The linear piece had a constant slope, so a horizontal line. This is actually turns out to be a piece of a parabola, and its slope turned out to be, its derivative turned out to be part of a line. So we see there. And this one here has this kind of a shape to it. And there's where we see 0 here, and positive slopes to the left, negative to the right, positive here, negative down here, and we see asymptotes here and here. Okay? So that's, if you have a graph like this, you should be able to determine some of the characteristics that the derivative graph would have. Maybe even draw it in by estimating the derivative at several points. Now the next one, I'm giving you some graphs here. And here's the graph of let's see, column A is an original function, and the next page will be all the derivatives, and maybe some extra ones that don't match up, because I think I've got more on the next page than here. So it says if the function looks like this, what does its derivative look like? If the function looks like this, what does the derivative look like? And then this, and then this. So I'll tell you what, and here are choices for the derivative. We got to find which one matches with which one. Okay, so I'll tell you what, let's just leave it like this for just a minute. Zoom in a little bit and leave these two up here for you and see if you can come up with what the derivative would look like for these two. Get a rough sketch of it, and then from your rough sketch, let's see if we can pick one on the next page that goes with each of these two right here, and we'll do the other two in a minute. Okay, so go ahead and work this out, see what the rough sketch would be, and then we'll go pick one out. So press pause now. Okay, well you're back. Do you have sketches of those two? Now let's look down here. You should have a sketch of what the derivative looks like here and here, just a rough sketch. See if we can match it down here. Do any of these look like the one that you had for the first one? Or the second one? Which one would you pick? Okay, let's see what I was going to say here. Okay, now if I were doing this, I would look at this and say, this is the original function, and what I want to find is the graph of the derivative. Well, let's see here if I can kind of do some really rough sketching in here. Okay, so here we see a local minimum, so the derivative is going to be 0 right there. Here we see a local maximum, so the derivative is going to be 0 right there. Here we see increasing function, so the derivative is positive here. Here we see increasing, so the derivative is positive there. Between, we see decreasing, so we see negative derivative. Changes from concave down to concave up somewhere in here. It's going to have this rough shape here. Now what I haven't done is graph points. I've really only graphed 2 points. So let's see if that's enough to pick it out from the ones there. Now how far down does it go? I don't know. I'm going to have to do some estimating. Let's say about here, how far down does it go? Let's do a rough estimate. So if we go left and right one grid line, let's say, it goes from about here, which is about 5, down to 0, so that's a drop of 5, so it's negative 5. And these are one space either direction, so that's divided by 2. So it goes down about negative, so it goes down about 2.5 negative. Okay, so let's see if I can do a little bit better drawing in there. Okay, so it goes here, here, negative 2.5 here, and so probably looks something like this, and there, and then it's going up from there. That's a really rough sketch, but let's see if we can find one that looks like that. Okay, so which one would that be? Oh, it looks like E. So down about 2.5. Yeah. 0 there and there. Yeah, it looks like E. Any others even close? No, that's the one. So that must be E. Okay. So we have E there. Okay, how about the next one? Okay. Now the next one looks like we have several max and mins. So we have a maximum here. It's like maybe it might be a trig function, like a sine or cosine. This is a minimum, so we have a 0 there. 0 here. Right here again. Right here. And right about here. So we know it crosses the x-axis at those places. What's this here? Okay, so what else do we see there? Well, let's see. The function is decreasing here, so we should see negative stuff between here and here. Looks like here is about the lowest it's going to get is the steepness is right around in here. Let's do an estimate there. So you go to the left, this goes up about 1.8, and to the right it goes down to about -2. That's a drop of about almost 4, right? So not quite 4. Divide by a delta x of 2, that's a drop of not quite 2. So it's not going to go down quite to -2, but somewhere in here, maybe it's going to do that. Looks like that place where it was the smallest maybe was about there. That's going to be our inflection point as well on the original curve because it's concave down here. So the derivative is decreasing, and then the derivative goes to increasing. So it goes something like that. And I think this one is going to go up about the same amount. And I think we're going to see something that looks kind of like that. That's a really, really rough sketch. But let's see if one of our ones in our picture looks like that. So let's see. We're looking for it crossing the x-axis around 0, maybe a little bit to the left of 10. Somewhere in here, somewhere out here, and here at the axis it's coming down, decreasing as it comes into the origin. Concave up here, concave down here, concave up here. Okay, let's see if one of those has that picture. F could be possibly. G's not. This is going the wrong direction. Okay, must be F. Now that looks like the one there. So it's like F for that example. All right, let's do a couple more. Okay, you look at these and then figure out what the derivative looks like. Sketch it, then we'll take a look and pick from our choices. Press pause now. Okay, at this point you should have a graph now of each of the derivatives, at least a rough sketch. See if you can find, does one of these look like the derivative of one of those, or maybe one of these? Does your graph look like at least one of these? Which one? Which one goes with which? Okay, let's work it out. Well, let's look at this one here. Well, what do we see? We see an asymptote here. So this is increasing, looks like it's increasing the whole way, which means the derivative is always positive. So the derivative is above the x-axis. Secondly, we have this is concave up, the original function is concave up, so the second derivative is positive, and the first derivative, which is what we're trying to graph, is going to be increasing. So so what do we have? We have this, the original function is here, the derivative is increasing and always positive. Kind of like what this one is. Okay, let's see what else we got. So as we go farther and farther to the left, as x goes to -infinity, this graph approaches a horizontal asymptote, which means it's getting nearly horizontal. Horizontal line has a slope of 0, so the farther out you get, the closer it gets to 0. So the derivative is also going to have a horizontal asymptote here. We could estimate right here. Looks like this goes up from left and right here at the origin, or at the x-axis. Looks like it goes up about 1.5. Divide by 2, that's about 3/4. So maybe a little bit below this. But it looks like maybe, maybe it has the same basic kind of a shape. Okay. Alright, let's see if one looks like that. Yeah, sure enough, there it is, B. That's the only one it could possibly be. So that's B for that one. All right, and let's do another one. So here we have a parabola. Notice right here, and right here, there's a horizontal tangent line. So that is, and it's a minimum. So there's a 0 there. To the right of this, the function's increasing here. To the left, it's decreasing. If this is a parabola, this would be straight. So maybe a straight line. You could estimate some points here and see what they might be. For example, right here, we go to the right one, we go up 1, 2, 3, 4, 5, maybe 6 or so, maybe more. And to the left is 1, 2, 3, 4, 5, almost. So that's like going up 11. Then with the delta x of 2, so that's like 5.5 or so. So in this one, so it's somewhere around here. Maybe it looks something like that, straight line. But certainly an increasing straight line, right? Let's see which one would look like that. It must be D. Okay. So we were able to match those up. Okay, here's a graph of a function. For what x values is this function non-differentiable? Where is it not differentiable? See if you can tell me. Well, it's non-differentiable anywhere it's undefined. So certainly at x equals 4, it looks like it's undefined there. It's also not differentiable anywhere there's a discontinuity, where it has a hole in the graph there with an isolated point at -2. But it's also undefined anywhere there's a sharp corner. It looks like we have one of those right there at 3. Everywhere else, it looks like it's pretty smooth, so connected, smooth, never vertical. So it looks like it's differentiable everywhere except for those values. So -2, 3, and 4, what we're looking for there. Alright, next I have a series of little true or false statements. So these are statements, you have to identify whether the statement is true or false. A, if a function is continuous at a point, then the function must be defined there. True or false? B, if a function is differentiable at a point, then it must be continuous there. True or false? And so forth. So see if you can read those on the screen there and work these out. When you have them worked out, come back and let's check them. Press pause now. Okay, let's read through these again and see if we can answer them as we go here. If a function is continuous at a point, then the function must be defined there. That is absolutely true. It must be defined to be continuous. If a function is differentiable at a point, then it must be continuous there. That's true also, which of course means it must be defined there and continuous to be differentiable. C is the converse of that. If a function is continuous at a point, then it must be differentiable there. That is false. We've seen some examples where that doesn't work. We just saw that, for example, in this last example right here at 3. It's continuous there, but not differentiable. We had a sharp corner. Could also happen if we have a vertical tangent line. D, a hole in the graph is also known as a non-removable discontinuity. That's false. It's known as a removable discontinuity. Why does it say that? Because you could remove the discontinuity by just filling in the hole, adding a point to it, or perhaps erasing one point and adding one. E, all polynomial functions are continuous functions. That is true. Okay, they are continuous functions, and not only that, they're continuous functions that are defined on all reals, so that makes them one connected piece from -infinity to infinity. F, the following types of functions are continuous at every point in the domains: polynomial, rational, power, exponential, and logarithmic functions. That's true. Actually, those are all continuous where they're defined, and the ones where they have some places where they're undefined, then they might particularly the rational functions and the power functions sometimes have those. Though, of course, at those points you have discontinuities, but at the points that they're defined, they're continuous. and all rational functions are continuous functions. That's false. They're continuous where they're defined, but they're not continuous at places where they're undefined. Now here we have another question. F prime of a equals the limit as h goes to 0 of pi over 2 plus h times e to the cosine of pi over 2 plus h minus pi over 2 over h. Does that look like a derivative definition in play? If it is, what would be the formula for f of x and the value of a in this scenario? See if you can figure that out. Press pause now. Well, remember the derivative a at a, f prime at a, is defined to be the limit as h goes to 0 of f of a plus h minus f of a over h. And so we need to look at this that way. Well, if you look, the a plus h looks like it's the pi over 2 plus h. So it looks like a maybe is pi over 2, and then this part right here is the f of a, right? And this part over here, the part over here is f of a, and that part might be f of a plus h. And the a looks like maybe it's pi over 2. Okay, so let's see if that's the case, what we've got here. So then f of a plus h is pi over 2 is a, so it's pi over 2 plus h, e to the pi over 2 plus h. So f of a and f of a is pi over 2. Now remember, f of a plus h is supposed to be this part. Okay, so it looks like this part is an x. So put an x everywhere you see the pi over 2 plus h. So there'd be an x here. Looks like that's x. And that is x. So then what do you get? That's looks like your function is x times e to the cosine of x. Now, if that'll work as long as we take that function and plug in pi over 2 and get pi over 2 out. So let's see what happens if we do that. Plug in pi over 2 for x here and here. That would be f of pi over 2. Cosine of pi over 2 we know is 0. E to the 0 is 1. 1 times pi over 2 is pi over 2. So that would work out just nicely there if we let x times e to the cosine of x be f of x and let the a be pi over 2. That one works out just nicely. In the last of these series of videos, we're going to look at some real-world interpretation problems for the derivative.